And that scaling is not decoration. Here's why it exists. A $1 fee spread over $100 million of liquidity is 10 to the minus 8 per unit. In plain integer math, that is 0. The fee just disappears. Shifted left 128 bits is comfortably representable. And then the last line, which is the interesting one for auditors. Tokens owed plus equals inside the unchecked block, with Uniswap's own comment sitting above it, shipped in production. Overflow is acceptable. You have to withdraw before you hit uint 128 max fees. So this can wrap. Okay, in Uniswap V2, when you provide liquidity, you get a token back, an LP token. It's fungible, it's tradable, it's the receipt. Go looking for that in the V3 core, and it isn't there. There is no LP token in Uniswap V3, not in the core. Your position is a hash and 5 numbers. This is section 6 of building Uniswap V3 on the Zealynx Academy, and it's where fees stop being a global number and become yours. So why did the token disappear? Because fungibility disappeared first. In V2, every liquidity provider held the same thing, a pro rata slice of the whole curve. Same asset, same payoff, different sizes, perfectly fungible, so one token per pair works. In V3, an LP on the range minus 100 to 200 and an LP on 200 to 400 hold genuinely different assets, different payoffs, different risk, different exposure. There's no single token that could represent both, so the core does the simplest possible thing. A flat mapping keyed by the hash of owner, lower tick, upper tick, hashing the triple into 1 bytes 32 costs less gas than 3 nested mappings, and it keeps addressing down to a single storage slot. And there are 2 consequences here worth internalizing as an auditor. First, adding liquidity twice, same owner, same range, merges into one position. There's no position ID. There's no count, same key, same slot. Second, and this one surprises people, the owner field is whoever calls the pool. For most real users, that's not them. It's the periphery's non-fungible position manager, which owns one giant bag of pool positions and tracks, who owns what by NFT token ID on top. So the NFT you see in the interface is periphery bookkeeping. The core neither knows nor cares. And look at what is not in the struct. No entry price, no timestamps, 5 fields, liquidity, 2 fee checkpoints, and 2 debts. Everything else is derivable. Now the other thing V2 did automatically that V3 can't. Compounding. In V2, fees accumulated inside the reserves, so every LP's share appreciated on its own. You didn't do anything. V3 can't. Fees belong to specific positions, whoever was in range when that fee accrued, while liquidity is a range-wide quantity. To compound a position's fees, you'd have to convert an arbitrary pile of token 0 and token 1 into perfectly ratioed range liquidity at the current price. That's a swap plus a mint, per position, on every touch, so V3 doesn't. Fees accrue as tokens owed, a plain debt the pool owes you, and sit inert until collect moves them. And if you want compounding, that's a periphery or vault problem, which by the way is where a long trail of V3 auto-compounder exploits comes from. It's a genuinely hard problem, and V3 declined to solve it in the core. Reading a protocol for what it deliberately does not do is a skill, and it's a lot of what we work on inside Zealynx Insiders. Live sessions every week on real code, and office hours where you bring your own. Links below. Right. The update function. It's a checkpoint-then-accrue machine, and there are 3 steps. Step 1. Cache and gate. Read the struct once into memory. That's cheaper than repeated storage reads, and it freezes the pre-update values for the fee math coming next. Then branch on the liquidity delta. And here's a thing you'll see all over V3. A call with a 0 liquidity delta is a poke. It means, recompute my fees, don't touch my liquidity. You'll meet the burn 0 idiom that triggers it in section 9. The require in that branch, NP, no position, rejects pokes on empty positions. And it's worth being precise about what it protects, because it's not what people assume. With 0 liquidity, the fee accrual is necessarily 0. Multiply any delta by 0 liquidity and you get 0. So no phantom debt could ever be minted, require or not. What the require actually stops is a poke on a position that doesn't exist succeeding quietly, writing checkpoint storage for a position with no liquidity, and letting a call with the wrong owner or the wrong range return as if it had done something. It makes non-existent positions unrepresentable in the fee flow. Touching one fails loudly. instead of no-oping convincingly. That's a different and better property. Step 2. Accrue. And you should read this one inside out. The subtraction is growth, since my checkpoint. 2 relative accumulators from section 4, so it must be free to wrap. Same unchecked argument as before, checkpoint 3. Current one after the global wrapped, 1 minus 3 wraps to exactly the right delta. Then multiply by the position's liquidity, and notice which liquidity, the PRE update value, out of the memory cache, because the fees being settled were earned by the liquidity that was actually in place, not by whatever you're changing it to right now. Then divide by Q128 to strip the fixed point scaling. And that scaling is not decoration. Here's why it exists. A $1 fee spread over $100 million of liquidity is 10 to the minus 8 per unit. In plain integer math, that is 0. The fee just disappears. Shifted left 128 bits is comfortably representable. That's what the X128 buys. 128 bits of sub-token precision, so tiny per unit fees survive integer division. Small numbers to make it concrete. Liquidity 5000. Checkpoint at 70 fee units per unit of liquidity. Current inside growth 90. Delta is 20, scaled. Multiply by 5000, divide by 2 to the 128, and you get 100,000. The position earned 100,000 way of token 0 while it was in range. Step 3, checkpoint and settle. And the order here is the whole invariant. The checkpoint is always overwritten. That's what makes the next delta start from now. But you accrue against the OL checkpoint first. And only then advance it. Invert those two lines and every position's earned fees vanish on every touch. Because if you advance the checkpoint first, the delta you then compute is current minus current, 0. Every time. Nobody ever earns anything, and the bug is completely silent. No revert, no wrong number, just a protocol where fees quietly never accrue. The two guards around the rights, by the way, are pure gas. Skip the storage right when nothing changed. They're not doing anything semantic. And then the last line, which is the interesting one for auditors. Tokens owed plus equals inside the unchecked block, with Uniswap's own comment sitting above it, shipped in production. Overflow is acceptable. You have to withdraw before you hit uint 128 max fees. So this can wrap. If you never collect, you can lose the balance. Why is that acceptable? Because uint 128 max way is about 3.4 times 10 to the 20 of an 18 decimal token in fees for one position. That's astronomically far from anything real. And the failure hurts exactly one party, the negligent owner. Never the pool, never the other liquidity providers. And here's the part worth sitting with. The alternative is worse. Checked math here means a wrapped accumulator reverts, which would brick burns for everyone. This is the kind of line you flag in an audit and then close as acknowledged. Knowing when a protocol is right to accept an overflow is as much an auditor's skill as finding the ones it wrongly ignores. Okay, let's write the two steps that carry it. The accrual, both tokens, current fee growth inside minus the checkpoint, times the pre-update liquidity, divided by Q128, cast down to uint 128. Every one of those 4 operations is a decision we just went through. The subtraction has to be allowed to wrap. The liquidity has to be the old one. The division is what undoes the X128 scaling. And the cast truncates silently, on purpose, for the same reason the addition is allowed to overflow. And now the settle. In order. Liquidity first, guarded. Then both checkpoints unconditionally always advance. That's what makes the next delta correct. And then the debts, guarded, with the overflow that Uniswap explicitly accepts. Read the order one more time. Accrue, then checkpoint. Everything above this line depended on it. The rest is the mapping keyed by the hashed triple, the memory cache, and the unchecked wrapper around both the accrual and the debt addition. And run it. 13 out of 13. So, positions are a hash and 5 numbers. Fees are a debt, not a compounding balance. And the ordering of tool lines decides whether anyone earns anything at all. Next episode, we finally open the pool itself. State, slot 0, and initialization, where all of these libraries get wired into one contract, and where you'll see why the pool packs 7 values into a single storage slot. See you there.